Um, so thank you everyone for joining. I'm really excited to be presenting this work here today, and I'll be talking about a variational autoencoder based method that we developed for identifying circulation regimes targeted to a local scale impact variable. And so I'll start by motivating why what drove us to develop a new method. I'll then go into a bit of background on different linear dimensionality reduction methods that you might be more familiar with, and then sort of what makes or how variational autoencoders are different or similar from that. And this is something I included because I found that I was going back to it quite a bit when I was presenting this as a poster at the CIDA General Assembly. But yeah, since this is a small group, please feel free to come in if there's anything that's not too familiar. So then I'll present the method that we developed and then go into the different sections of the results that I'll explain as we go along. So the motivation of this work was the question of identifying dynamical drivers of extremes or representations of dynamical drivers of extremes, and this is useful for a range of reasons. Amongst them, that dynamical drivers can be sources of potential predictability at S to S, sub-seasonal to seasonal lead times, or longer, and that they can also help us understand or physically understand climate model uncertainty better. So these are just some reasons, and one way of understanding or representing these dynamical drivers in the mid-latitudes is in terms of discrete, persistent, and recurrent circulation patterns, which are called weather regimes. So the most widely studied the region where weather regimes have been the most widely studied is the North Atlantic. So I'll use that as an example to explain what weather regimes are. Weather regimes are commonly identified by first dimensionality reducing a space such as geopotential height at 500 hectopascal and then clustering it. And usually this is done using principal component analysis combined with k-means clustering, or this has established itself as something of a standard. And if you compute these regimes over the North Atlantic, you get predominant patterns of atmospheric variability over this region. So you get the two phases of the North Atlantic oscillation, a Scandinavian blocking pattern, and an Atlantic ridge. And these figures are taken from a paper studying impacts of weather regimes on renewable energy production. And what you see, and in the upper column, you see wind anomalies associated with these weather regimes. And what you see is that the NAO in particular has large impacts on wind over the UK, which is why we in the UK like to study the NAO. But we also see that there's a lot of regions where this predominant pattern actually doesn't have that much of an anomaly associated with it. So the challenge that we're trying to address here is that weather regimes identified using dimensionality reduction and clustering don't necessarily capture the dynamical processes that modulate our extreme of interest. So there have been other approaches to study targeted circulation patterns that either rely on filtering extreme days, because then you sort of have a subset of days that you're trying to identify predominant patterns in, clustering the impact variable directly, increasing the number of clusters, or, for example, projecting using a linear dimensionality reduction method such as CCA, which I'll go into more detail later, to jointly dimensionality reduce the target variable and, for example, the geopotential height space. But in some way or another, these different methods risk compromising the predictability of the regimes themselves, which is the reason that we're interested in studying them in the first place. So the research question that we ask here is, can we identify atmospheric circulation regimes that are more informative of the impact that we're interested in, so that disentangle the dynamical patterns that lead to the extreme of interest, while still providing a full representation of the atmospheric phase space and maintaining the predictability of the regimes themselves. And inherent in this question is something of a tension between the aim of dimensionality reduction, which is to identify an optimal reduced space to capture the dynamics of a higher dimensional space, and the aim of regression or prediction, which is to identify an optimal set of predictors for a given target variable. So the way that we address this question is that we developed a method based on a variational autoencoder that combines a dimensionality reduction or probabilistic dimensionality reduction that is regularized using the target variable with probabilistic clustering in a coherent statistical model. And the results that I'll be presenting here are in parts published as a preprint and accepted for publication in environmental data science, and they're in other parts being written up at the moment to be submitted. Also to note that the code for the results that are published is available on GitHub if you want to have a look. So the target that we're looking at here is extreme precipitation over Morocco in extended winter, which can lead to a range of different types of flooding in different parts of the country. What you see here in the lower picture is a k-means clustering of precipitation in extended winter, which gives us the predominant spatial patterns of extreme precipitation. And we see that in the pattern 2, pattern 2 is associated with no or very little precipitation and accounts for 80% of days, while patterns 3 and 4 are much less frequent and much more associated with extreme precipitation days. And in terms of dynamical drivers of extreme precipitation over Morocco, this has been studied in terms of circulation regimes over the Mediterranean region, as well as over the North Atlantic region. And while regimes in both of these regions show some modulation or somewhat modulate extreme precipitation, there are also more detailed studies of dynamical drivers of extreme precipitation that show much more localized patterns which are not resolved in the regimes over these two regions. So this provides our motivation to apply the method to Morocco. And just sort of to frame this talk, or to frame what we're trying to do here, we're asking if these targeted circulation regimes represent suitable mediators that are predictable, that capture or that are informative of the local impact, while still being modulated by sources of predictability in the climate system. Just in terms of data, we use 5-day average geopotential height at 500 hectopascal over the North Atlantic Mediterranean region, shown on the right. In ERA 5 reanalysis data from 1981 to 2022 in extended winter. And we use this this shorter time period because it's the time period over which the precipitation data set CHIRPS is available, which combines satellite-based observations with on-the-ground observations, and is a more accurate representation of precipitation than ERA 5, at least. I'll get to how exactly we use precipitation in the method in a moment. So just to give a bit of background on linear dimensionality reductions, and I'll go through this quite quick given the audience. So the most widely used dimensionality reduction approach in atmospheric sciences is principal component analysis, which is a linear projection of a high dimensional space onto the eigenvectors of the covariance matrix. And this is sort of an illustration of this. And canonical correlation analysis is a linear projection of two related high-dimensional spaces onto basis vectors, such that the correlation between those projections are mutually maximized. So both of these methods are linear dimensionality reduction methods, and to some extent solve different eigenvalue equations. Now, you can think of principal component analysis as learning an encoder into a reduced space, or a linear encoder into a reduced space, and a linear decoder back into the reconstructed space, for example, using the first 10 principal components. And you can think of an autoencoder as a nonlinear generalization of this idea, where the encoder are several neural network layers, and the network is fit, in the case of an autoencoder, using the reconstruction loss. So an autoencoder sort of trains the weights of this neural network to encode as much information as possible in this reduced space. However, an issue with this is that the reduced space identified by an autoencoder is not necessarily continuous, and therefore not, which is not great for clustering or identifying regimes. So a variational autoencoder extends an autoencoder by explicitly fitting a probability distribution into the reduced space for the purpose of regularizing it, or by regularizing it. What this means is that the variational autoencoders therefore provide a continuous reduced representation that can be used to generate new samples of the data from the reduced space, which is why it's referred to as a generative deep learning method. So this probability distribution in the latent space is fit using Bayesian variational inference, and regularized using a prior distribution, and the prior distribution is often chosen to be a multidimensional Gaussian distribution. So the reasons that we chose to work with a variational autoencoder are that the principles underlying how the loss function of this architecture is derived using variational inference allow us to extend the statistical model that we fit inside the reduced representation. And second is that the variational autoencoder has been applied to study weather regimes and shown some promise there. So this is an illustration of our architecture, and the architecture extends a standard variational autoencoder architecture in two ways. So as the input data is the Z500 anomaly, or the Z500 anomalies that I showed you earlier, we have an encoder, and then instead of fitting a single Gaussian, we fit multiple Gaussians. So we fit a Gaussian mixture model directly into the latent space. So we combine dimensionality reduction with probabilistic clustering. But we also, from the encoder, predict the target variable and use this to regularize the latent space. And what this does, or why this helps target the dimensionality reduction, I'll show you in the results later. But for now, there's two variations that we developed of this method, and they differ in how the target variable is represented, because we're using the target variable for regularization. We need to compress the information about the target variable in some way, and we do this either by using the spatial average over Morocco as a target variable in the regression mixture model variation autoencoder, or by using the spatial patterns, which are shown here, which are the same ones we saw on the slide earlier, which are identified using k-means in the categorical mixture model variational autoencoder. I thought I'd show this here to sort of to show the loss function here, just to illustrate that we can represent what's illustrated in the figure on the slide before as a graphical model and show how so sort of how a regular variational autoencoder tries to fit a reduced space Z based on an input space X. And the way in which we extend this here, if you look at the, for example, the middle graphical model, is that we not only try to estimate the latent space, but also C, the cluster assignment, and T, the target variable that we then use to regularize. And based on this, or writing this as a graphical model, we can derive a loss function for this architecture, where the different terms in the loss function represent the different objectives of our architecture. So we have the reconstruction loss, so the aim of the architecture being to find a representation of the atmospheric phase space. We have the regularization loss, a regularization of the cluster probabilities, sort of a regularization of the cluster centers, so of trying to find cluster centers that capture maximum variability in the reduced space, and the prediction loss. And the only prior that we have to, or that we set here, is first of all the number of clusters and the fact that we fit them as Gaussian distributions, and second, the prior we set on the cluster probability. And here the prior we set is that all clusters are somewhat equally frequent. So this isn't a hard constraint, but sort of guides the optimization into not just finding one cluster for everything. So in our results, we compare this new method to the two linear dimensionality reduction methods that I showed earlier, and implement this architecture in a fairly standard way, as you would a regular variational autoencoder. So the main difference here is the loss function that we use and derive. So if we look at the regimes that this architecture identifies over the North Atlantic and Mediterranean region, we can start by looking at the first row, which is the regimes identified using PCA and k-means, and we find that we find the clusters we somehow would expect. So we find the two phases of the North Atlantic oscillation. We find something that looks like a Scandinavian blocking, an Atlantic ridge, and sort of an opposite of the Atlantic ridge regime. If we then look at the bottom row, which are the CMM regimes, we find that the method identifies, if you look at regimes 2 to 5, sort of quite similar patterns. So we have, again, the two phases of the NAO, an Atlantic ridge, and something that looks like a southward shifted Scandinavian blocking. However, we identify an additional regime, which is a Scandinavian blocking associated with some form of a cutoff low off the coast of Morocco, which is actually associated with the highest increase in extreme precipitation. And what you see in the sort of in the lower rows here is the odds ratio of extreme precipitation, so exceedance of 95th quantile of precipitation, 95th percentile of precipitation over a specific grid point given this regime. We find that using we find that using a CCA in this particular case helps us identify regimes which are predictive of precipitation, but that overall less structure in the atmospheric phase space is identified, because CCA projects the data onto a subspace that's optimized for correlation with precipitation. We tried this method over different regions and sort of find and the CMM method is able to find a pattern that looks similar to this in different in different choices of the box. We can also quantify the informativeness of the regimes of precipitation by constructing a prediction from the regime to precipitation and evaluating this prediction using the Brière skill score. And we can do this for precipitation clusters and exceedance of the 95th percentile threshold over the entire region. And we find that the CMM regimes perform better in terms of the skill score, which means that they are more informative of our local target variable. So yeah, okay, I've said this. Okay, so yeah, these are the findings we can get from that. But then the second, and to sort of investigate why this might be the case, we can look at the reconstruction loss of the method and find that we use the same number of reduced dimensions for all three methods, and we find that the variational autoencoder with sort of the nonlinear function that it can fit in its encoder is able to encode much more information per latent dimension, and we find that CCA with its projection into a partial subspace is not able to reconstruct the full phase space as well as principal component analysis, which is sort of to be expected. And then sort of going back to the feature of or to the way that the method uses the target variable to regularize the latent space, we can visualize the reduced space itself to see how the target variable is organized in this latent space. And this is a TSNE visualization, which is sort of commonly used in machine learning, and it's a sort of nearest neighbor dimensionality reduction method that's mainly used for visualization purposes. So it shouldn't be overinterpreted, but sort of what we're trying to do here is trying to visualize the 10-dimensional reduced space in 2 dimensions. And then the upper row, we see the individual data points colored by the amount of precipitation that they're associated with. And in the lower row, the cluster or the regime that these data points are associated with. And you see a method here that I haven't mentioned before, just ignore it. It's because we were combining results from different papers. So what you see here is that if you look at the upper right corner, you see that the targeted dimensionality reduction basically organizes the reduced space in terms of the target variable, or in other words, or sort of in machine learning words, you could say it, the method disentangles the dimension in the geopotential height space associated with precipitation over Morocco. And therefore the subsequent clustering is able to or finds clusters that are more coherent in terms of their precipitation response. Okay, so now we've shown that with this method we're able to identify clusters which are more informative of the target variable. But in order for these targeted regimes to be suitable dynamical drivers that we can use to improve S2S predictions, the drivers should be predictable themselves. So we investigate the predictability of these different regimes in subseasonal hindcasts and evaluated using, again, the Brière skill score extended to a multi-category forecast and the receiving operator characteristic area under the curve. And in both cases, higher values are better. And what we find here is that the targeted regimes are overall as predictable as the PCA regimes, which sort of can be interpreted as that the partitioning that the CMM regimes identify of the atmospheric phase space doesn't, or is as predictable as the partitioning identified by PCA, whereas the clusters identified using canonical correlation analysis and then k-means are slightly less predictable. To further investigate the predictability of the targeted regimes, we now come back to the figure we saw at the beginning. And investigate subseasonal drivers that are known to influence the Western Mediterranean region at subseasonal lead time. So we investigate variability in the stratospheric polar vortex and the Madden-Julian oscillation, and see whether these two teleconnections modulate the targeted regimes in sort of a way that is physically interpretable or aligned with our physical understanding. And the aim of this is to see whether the targeted regimes are somewhat statistical artifacts, or maybe not, like they lump together points that have a similar precipitation response but share nothing else in common, for example. So to understand whether these targeted regimes are suitable mediators between local impacts and longer range sources of predictability. So the first way in which we do that is that we compute the conditional probability of the regimes given different phases of the MJO and the stratospheric polar vortex. So we'll start with the stratospheric polar vortex. So what you see here is lead times from 0 to 47 days, and the change in conditional probability of the regime given in each sort of small box, a weak vortex, a neutral vortex, or a strong vortex state. And we find here that a negative or a weak stratospheric polar vortex leads to an increase in the probability of an NAO minus like regime, which we find in both PCA regimes and the CMM regime, and that the sort of inverse effect is in the CMM regime split up between two different regimes, but also found so that we can say that the SPV teleconnections that we find in the traditional regimes are also represented in the targeted regimes. And every box that is sort of has a black box around it is a change in conditional probability that's robust to subsampling across years. So that could mean different things. That could mean either that this subseasonal teleconnection is modulated by a seasonal teleconnection, also if it's not robust across years, or that it's maybe a spurious effect. So this is the same figure just for the MJO, and I'll not go into too much detail explaining it because I think I'm running out of time, but happy to answer questions about this. And we can summarize this, or we can assess this effect of the subseasonal teleconnection on the regimes in terms of an information theoretic measure of predictability. And we look at different ones, and here I'm showing the change in conditional entropy in the regimes associate if we know the state of the stratospheric polar vortex or the MJO. And what the conditional entropy measures is the amount of uncertainty remaining in the regimes, given that we know the SPV or MJO. And so the higher values mean that there's more uncertainty remaining, and we find that the CCA regimes capture less information coming from the stratospheric polar vortex or the MJO compared to the targeted regimes or the PCA regime. So to summarize, to recap all of this, we introduce a new method for identifying atmospheric circulation regimes targeted to a local impact variable. This method is based on a variational autoencoder architecture, which combines targeted dimensionality reduction with probabilistic clustering in a coherent loss function that's derived using Bayesian variational inference, we find that the method identifies patterns which are more informative of the local target variable, and capture a more localized pattern leading to extreme precipitation over Morocco. However, we also see that these targeted regimes still maintain their overall predictability at subseasonal lead times and represent known physical teleconnections to the North Atlantic and Mediterranean regions. So overall, we conclude so far that the CMM method is able to identify suitable dynamical mediators between local impacts and teleconnections that can potentially be used to improve subseasonal teleconnections. Thank you for your attention, and I'm happy to discuss.
Thank you, Fiona. Please raise your hand with the chat or just ask your question to Fiona directly. Yes, Pascal?
Yes, hello, thank you for your presentation. So I have maybe a small question. So if you change the size of the domain for the weather regime or definition, would it affect the whole architecture or the encoders, or is it sensitive to the size of the domain?
Not so much. I think so when trying it over, I think the only thing you could change is the number of reduced dimensions that you choose. But I think you would do the same thing for principal component analysis, that the number of principal components you choose. So I think that's the only thing we changed.
Okay.
Yeah. But maybe also to elaborate more on that. So the pattern that we find over the region that I showed is similar to the pattern that we find if we, for example, just focus in on the Mediterranean region around Morocco and then compute anomalies of Z500 over a larger region. Obviously, then the Scandinavian blocking is not as prominent because it wasn't included in the dimensionality reduction, but it seems sort of consistent across the choice of box. Obviously, if we choose a very small region and increase the number of clusters that we study, like for example, if we choose the Mediterranean region and have, I don't know, 15 clusters, then PCA will also be able to identify this pattern. I think the aim here is to see if we can sort of identify the pattern relevant for, in our case, Morocco, without compromising the predictability of the regimes or increasing the cluster number so much.
If I may, I skipped a point, so maybe it was in your presentation and I didn't pay attention. So do you plan to do this with, let's say, CMIP6 or in a climate change context to be... So if you did this with, let's say, multiple models, did you see a dependence of the response to the models?
So we haven't done that yet, and you didn't miss it. I think that would be really interesting to do. I think yeah, that would be really interesting to investigate, and also to disentangle a bit, because I think for one, the model might be representing or not representing the patterns in the same way, or like the might have the let's say bias in the model might be in the teleconnection or in the relationship regime precipitation. So I think there would be a bit like some things to investigate there, but I think that would be really interesting.
Thank you.
Thank you. Please go ahead, Juliana.
Hi, Fiona. Nice to see you again. I had a question. Actually, I wanted to see the slide where you have your Bryan's-Q score for the model, because this is result I didn't know.
For the reforecast or
yeah, for the reforecast.
Yes, one moment. You can still see my screen, right?
Yeah, I see the thank you slide.
Okay, I'm here. You mean this one?
Yeah.
Yeah? Okay.
Yeah.
Okay.
Yeah, because I mean, comparing to the Bryan's-Q score that you showed before, just the one from the observations, right? That one is really like convincing that it's that CMM-VAE is much better. Like, do you have ideas for why is it starting from like lead 5, lead time 15? Is it so too close to the other methods?
So if I understand your question correctly, I think it's important. So we're using the same metric, but investigating different things. So when we're looking at the reanalysis data, we're looking at the relationship regime to impact.
Okay.
And see that the skill score for CMM is higher there, and that the regimes are more predictive of the impact. But here, and this may be a point I didn't make clear enough, we're looking at we're no longer looking at regime to impact, but we're looking just at the regimes and looking at, can we predict the regimes themselves? So not can we use the regimes to predict the impact, but can we predict the regimes themselves? And the reason that it's complementary, not complementary, but sort of the the complementary question to what we explored earlier. So because a lot of other targeted clustering methods can compromise regime predictability, and if you find very localized patterns that are no longer predictable, your targeted regimes might not be of that much use, because then you have targeted regimes that are super informative of the impact, but not predictable themselves anymore. So here we were just checking or just looking, okay, are we losing predictability? So actually, by targeting the regime. So actually the fact that they are equally predictable was a really cool result for us, because it means that even though we have more information about the target variable in them, we're not losing any.
Okay, got it.
Yeah.
Oh, okay, thank you.
No, but that was that's a good point. Thank you for asking that question, because maybe I wasn't making that clear.
Thank you. Any other question for Fiona? Okay. If this is clear enough, maybe we can wrap up here.
That sounds really good. If you have any questions, also feel free to email me afterwards if anything comes to mind.
Absolutely. Do you have anything to add?
Sorry. Hi, Fiona. Sorry, Manon, is it still okay? Or were you just about to?
No, absolutely. Go ahead.
Sorry for jumping right in. I was just, I know, or we didn't really talk about this yet, Fiona, but with the Valencia flooding, because it reminded me, of course, the cutoff law or the data. I didn't look into it so far. But I was wondering, let's say, assuming we would have the targeted circulation regimes for Valencia, kind of what benefits could it give us? Or do you think they could have been better predicted? Or, did you?
Yeah, I think, I thank you for that question. And I've had that on my mind as well. I think the one, at least from my sort of reading of it, is that the one thing that's one learning is definitely that even with good predictions, you need good early warning systems and so on, so that what we're doing is not it's not the whole thing. But I think so I think there's several things. I think one is that we could, or there's a couple of papers that use regimes over the Mediterranean or North Atlantic region and sort of do conditional predictions of extremes given a forecast of this regime. And I think, I mean, Emmanuel is on this call. I think maybe I think you did something like that in your PhD. So I think that would be an immediate way of using these targeted regimes that might be able to extend the forecast by a couple of days. I think to really then improve forecast at sub-season or seasonal lead times, it would be then important to perhaps build or extend the model to include teleconnections such as the SPV that give extended, like really extended range predictability beyond medium range. So I think yeah, those are the ways that I see for near-term prediction. So either sort of in a very direct way doing a conditional forecast, or sort of in a more hybrid approach. But then I think going back to the question of Pascal and looking at this in climate model data might also be a way to understand if these kinds of events are going to be more common in the future and so on. So.
Very good. Thank you. So we still have time if there is any late other question or anything to add. Yes, Juliana?
Yes.
Okay, so since there is some time, I have another question in comparison to your other method, to the RMM.
Mm-hmm.
So when you went through like the different, you compared to your causal, your graph.
Mm-hmm.
So the difference for you in comparison to the RMM is that instead of having a target variable that you regress, you have then the prediction of to which cluster it belongs. I didn't really.
Yeah, no, I didn't go into the details of that because I thought it would be too detailed, but I'm happy that you asked. So the so the question is essentially, how do you define your target variable well, that it sort of encompasses as much information as possible in as little dimensions as possible, essentially, to be used for regularization. And in the RMM, we have a regression to the mean of a scalar variable, and then use this scalar variable to regularize, and that this is what's shown here in the middle. We use the target variable to regularize the latent space directly. And the reason that we then thought of this alternative CMM method is that we thought that a categorical variable such as spatial clusters of extreme precipitation is another way of capturing information about extreme precipitation over Morocco, but you can't use this categorical variable to regularize the latent space directly. So sort of the modification to the architecture is that we, instead of a linear regression, we do a logistic regression to the target variable, and then we regularize not the latent space directly, but the cluster assignment C. So sort of the regularization is not on the latent space, but on the cluster assignment, which makes it fit for using a categorical target variable.
Got it. Thank you. Got it. Thank you.
Thank you. Any other point to the couple of last minutes? Okay. If it's fine, if it's, we can wrap up here. And thank you very much, Fiona.
Thank you all for joining.
And I'll see you next time, next webinar. Have a good day. Thank you.
Bye bye.